Hi students, now we are going to understand what is conservation of angular momentum. So in the previous chapters, we have studied conservation of linear momentum. So let us give introduction to the conservation of linear momentum in terms of translatory motion. So in translatory motion, first of all, what is the statement of conservation of linear momentum? If the external force acting on a system is 0, then the total momentum P total remains constant, both in magnitude as well as direction. So in the absence of an external force, the total momentum of a system of colliding bodies will be a constant, and F is equal to what? dP divided by dt. That is, the external force is equal to the rate of change of linear momentum we have studied. So this implies if F is equal to 0 means then dP by dt is equal to 0. Therefore, what is that P is equal to constant. The same is getting repeated in terms of what? Rotational motion. So in rotational motion, so which term is analogous to force in translatory motion? Yes, it is the torque. So in translatory motion, force is equal to the rate of change of linear momentum. Like that, in rotational motion, torque acting on the body is equal to dl by dt, where L is the angular momentum. So dl by dt means what? Rate of change of angular momentum. Okay. So in the same lines, if you take if tau is equal to 0 means then d by dt of L is equal to 0. What is capital L? Capital L means angular momentum. So capital L is equal to I omega is called angular momentum. Linear momentum is the product. See, already we have studied P is equal to M into V. Is it that? Mass into linear velocity. So in place of mass, the analogous term is moment of inertia in rotational motion, and that term analogous to linear velocity is angular velocity omega. So capital L is equal to I omega is the angular momentum of a rotating rigid body. So in this equation, if tau is equal to 0 means then dl by dt is equal to 0. Okay, or the rate of change of angular momentum is substituted by I into omega is equal to 0. So d by dt is a differentiation of a physical quantity I omega. When the differentiation of a function is equal to 0 means then the function must be a constant. Is it not? So from this equation, therefore I omega must be equal to a constant. So this is the mathematical expression for the conservation of angular momentum. I into omega must be equal to a constant. Or I can write therefore omega is inversely proportional to I. So omega is inversely proportional to I. Understand? So I initial into omega initial must be equal to I final into omega final, and this must be equal to a constant. So we can also represent omega is inversely proportional to I. How? What do you mean by this equation? When the moment of inertia, that is, if moment of inertia increases means then omega is the reciprocal, is it not? Is proportional to the reciprocal of moment of inertia, so that omega decreases. The speed of rotation will decrease. Understand? If the moment of inertia decreases means then the speed of rotation, angular speed of rotation will increase, such that always this product of I into omega will be a constant. There are so many interesting examples from which we can understand the conservation of angular momentum. The very best I am telling you, children, you see the planetary motion. All planets revolve around the sun in our solar system in an elliptical path, longer circle, okay, elliptical path. So sometimes our earth is coming very closer to the sun, and this position of the earth when it is very close to the sun is called perihelion or perigee position, perigee, okay. And whenever the earth is going at a farthest distance from the sun, that farthest position of the earth is called as what? Aphelion. Okay, it is far away from the sun. It is also called apogee, apogee, very far position. So the near position of the earth when it comes closer to the sun is called perihelion. Okay, now you take the axis of rotation is passing through the sun, sun as the center. Okay, axis. With respect to the axis passing through the sun, the distribution of the mass, of this two particle system, sun earth system is now called as a two particle system, so that the distribution of mass is away, so that here in this case moment of inertia will be maximum, and hence the angular speed of rotation will be minimum. So when the earth is passing around the sun at this apogee position, the angular speed will be very less. So it will go very slowly, it will turn very slow. And at this position you see the same two particle system, the mass of sun and the earth together will be the same at any position. But the distance of separation between the earth and the sun is very less. So the moment of inertia decreases. At this position, the moment of inertia will be minimum. So I is minimum. Therefore, the speed of rotation will be maximum. So whenever the earth is coming closer to the sun, very fast it will cross the sun. And whenever it is farthest from the sun, it will move very slowly. So the planetary system in our solar system, okay, this is obeying the law of conservation of angular momentum. Not only this, even sometimes the electron revolving around the nucleus also, conservation of angular momentum is true. Like that, in so many other examples also, we can understand that if the external torque acting on a system is zero, then the total angular momentum of the system remains constant. So this is the statement of the law of conservation of angular momentum, and it is similar to that of the conservation of linear momentum in the translatory motion. I hope you must have understood well. Fine.